All right, so we're going to start with 11.2 today, and that is what we worked on in 11.1, systems of linear line equations, but only two variables, and therefore we only needed two equations for that system. Now we're going to up the ante a little bit here in this second section and add a third variable, which you should all know means we need a third equation. Okay, so hopefully you remember most of this stuff. This is things that you should have seen in the past, but just a quick overview. And again, I'm going to record this so that you guys can pause it and read all of this if you'd like. But what we're going to be trying to find is still that solution that works for all three equations at the exact same time. And that, instead of called an ordered pair, is going to be called an ordered triple. Because instead of an x and a y, two things that work for those two equations simultaneously, we're now going to have an x, y, and z. Okay? So what we're going to talk about is where those three planes, like a piece of paper, a wall, where would they all meet? If you can look around and there's two side walls and maybe the ceiling, look at where all three of those intersect. If you look at two of them, it would be an entire line. But if you look at the third, there will be a corner, a point in your room. And that's where they would all meet, at that X, Y, and Z plane point. Okay? But I wanted to show you what these things look like, just in case you're in your closet or somewhere that you might not be able to see. All right? For these new 3x3 systems. Cool thing is we'll still use our substitution and elimination techniques, all right, algebraically. And remember, we didn't really like graphing. Well, we're definitely not going to like graphing if it's in 3D. All right, I see Emily brought her 3D glasses, but not all of you may have those on, okay? So now we have three different planes for these three different coordinates. And so again, if you were to look at all three different colors of those planes and any line on it, they would meet at that one individual point, which we're going to again call an ordered triple. All right, order for the alphabet, triple because there's three. Okay. Now there can be some special things that happen where they all meet on a line. So we have the infinite number of equations or solutions again for those equations. So we'll list those accordingly. But then there can also be no solution, something that doesn't work for all three. Obviously that, where they're all parallel to each other, just like before. But then there could be two parallel and then that one. There's not a point that works for all three. Same thing here. All right, so this would be that no solution situation. This would be an infinite number of solutions, but only along that point, that line, excuse me. And then what happens most of the time is they meet at that one point. Some X, some Y, some Z. Okay, so instead of just having X and a Y axis, now we're going to have this Z axis going up and down as well. Okay, it's just hard to draw on a two-dimensional surface. All right, so that's the good part. There's your notes. There's nothing really new to this other than the fact that we have three equations and three unknowns. So I'm going to start you off with an example of the substitution method. We'll start with that one first. Okay, and if we're going to use the substitution method, remember that means we want to be able to state one of our variables. And obviously in any one of these three, you can choose to solve for the X, the Y, or the Z. The X, the Y, or the Z. But when are we going to use substitution? Definitely when we know one of our variables. And in this case, in equation 2, we can see Z is all by itself. So then what would I do to that equation 2? And I'm going to label them just so that we can still talk about them. Okay? I'm going to take equation 2 over here, and I'm going to take that 2x plus 4y, plus z equals 16, and I'm going to solve for z. And I'm going to start by subtracting over. Since they're positives, I'm subtracting. Just because you subtract doesn't always get rid of things. And by doing that, it cancels those two things out on the left and leaves me with the z, which is 16 minus 2x minus 4y. And that's still my equation 2, just in a different form, solved for z. Now guys, do we know how to really solve 3 equations with 3 unknowns? Did we really know how to solve in the previous section, 11.1, 2 equations with 2 unknowns? Not really. That's why we use substitution and elimination. It was to get rid of one of the variables, to get it down to 1 equation with just 1 variable. That's really all we know how to solve. So our task when we have 3 equations and 3 unknowns is to get it down to 2 equations with 2 unknowns. Because then we know how to solve that by getting it down to just 1 variable in 1 equation. So that's the goal. All right. So what I'm going to do is I'm literally going to take equation 1 and equation 2. And let me see if I can do this quickly. Nope, not going to work. All right. Just trying to do a shortcut here. 3x minus 4y plus 2z is equal to negative 15. We know that. We also know equation 3 is 2x plus 3y plus 5z. But instead of writing the z just like before, I'm going to put a big parenthesis in place of it. Maybe a little bigger. And I'm going to have that equal to the 20 that it was. And what am I going to do? I'm going to substitute in what I know z is equivalent to. This is my answer for z. But I need to know x and y in order to tell you what z is. But I do know that the z in this equation is the same as this. So I'm going to substitute in that 16 minus 2x minus 4y for that z and this z. Just like we did before. It's just a little bit more extreme for the 3 equations, 3 unknowns. Okay? And of course, what I'm going to do with that is just clean it up a bit, starting with doing what it says, order of operations. Nothing I can do in the parentheses. There are no exponents, but there is some multiplication to those parentheses. So I'm going to distribute. I'm going to bring down my 3x and negative 4y, but I'm going to take that positive 2 and distribute it to get 32 minus 4x minus 8y still equals my negative 15. Don't just keep doubling everything because you can. All right, it was only to this set of things, that z that we replaced. And then the third equation, I'll do something similar, but now I'm going to distribute the 5. And we know 5 times 16 is 50 and 30 for a total of 80. Negative 10x, negative 20y still equals 20. Now all I'm going to do is clean those up a bit by taking all the like terms, in this case the x's, for my equation 1 would give me negative 1x. If you want to write the 1, you can. Then the y's, which remember if you owe 4 y's and then you owe 8 more, you're going to add and still be negative to owe even more y's, which in this case would be 12. And then I don't even want that 32 on this side, so I'm going to go ahead and subtract it over to the other to get that to cancel out. And so now I have my new equation 1. So let me give a little more space here. Of the negative x, negative 12y equals negative 47. Now it's a lot of negatives, and I don't like negative people, negative things. So in this case, I'm gonna, because I can, multiply this equation all by a -1, the whole thing. And that would give me a new blue equation of x plus 12y equals 47. Now I'm going to do the same thing over here with equation 3, and I'm going to collect the x values, which that would give me -8x. I'll take the y values, which would give me -17y, and then I'm going to subtract over that 80 to have it all one side of my equation with the variables and the other with the constants, the numbers. And that, again, we can go ahead and multiply by -1 and get my new equation 3 to be 8x plus 17y equals 60. And if you guys can see what I now have should look very familiar to what we had previously. Our two equations with two unknowns, and now we should be able to solve. No problem. Okay? Now, since I committed to substitution at the beginning of this, does that mean I have to use substitution and solve for this x by subtracting that over and then plug it in there to find? Or could I change it over and do elimination if I wanted? Good. Emily and Brianna, you're absolutely right. I can take whatever technique I want and mix and match. So once you get to the two equations with the same two variables, in this case it's x and y, doesn't always have to be those two, but they do have to be the same, can I solve for the x or the y that are left by using elimination now? Or do I have to continue using substitution? Good news is, guys, it's your choice. Okay? So what do you want to do? Do you guys want to stay with the substitution because we can? This one is set up pretty nicely. And solve for this x and then plug it in for this one so that we have just one equation with y's in it? Or would you rather try to eliminate these x's or these y's? Which definitely, if we're going to choose the x's, right? Never thought I'd say that. Hopefully my wife isn't around. All right, so what do we guys want to do? It's up to you. Substitution, elimination.
Elimination.
Let's do it. So that means I'm going to have to do what in order to get something to eliminate?
Multiply one of them by a negative.
I'm going to go ahead and take this one because I know I can get it to be not just an 8x, but a -8x. And that's why we chose that. I'm going to multiply everything by -8. So that then gives me a -8x. 8 times 10 is 80. 8 times 2 is 16. That's a total of -96 y's. And if it starts to get too big to do in your head, go off to the side, use your calculator. But 8 times 40 is 320. And then 8 times 7 is 56. So that would be -376. That's how I do things in my head. I just break it up into parts. Okay? Now I'm going to take that new equation 1, and I'm going to write it right under this one. And again, feel free to use your calculator at this point. But now we're going to use that addition or elimination method by adding, since we know this is equal to this, and that is equal to that. If we were to add this side and add that side, then we know it should still be equal. Okay, so that's where it gets its name, the addition method. We did what we could to eliminate. All right, so that will eliminate those, and -96 is definitely going to win that battle, so it's going to be negative. So I'm just going to find the difference between 96 and 17, which would be what? See Brianna using her calculator. 96 minus 16 would be really nice, right? That would just be 80, but we have 17, so it's going to be
79.
Yeah. See how I did that? I knew 96 minus 17 is going to have to borrow, so I just changed it to a 16 and then another 1. And that's what I subtracted, because I know 96 minus 16 is 80, and then I just subtracted 1 more. Okay? Then we can also do this one in our head. Not too bad. Definitely the negative is going to win over this because it's the bigger number. So it's also going to be negative. And then 376 minus 60 would be 316. And at this point, what do we really hope? And keep in mind, everyone, I started with 3 equations and 3 variables, 3 unknowns. I had to do quite a bit of work just to get it down to 2 equations with the same 2 unknowns. But once I got it to there, it should be simple. We chose to use elimination. We eliminated. What have we finally got it down to? 1 equation with 1 variable. And that's the only thing we actually know how to solve. Okay? So what is being done to that y? It's being multiplied. We therefore will divide. And I'm sure Emily, Brianna, and hopefully everyone else that's following along already did that in their head. Positive 1y, and this would also be a positive. And if I had to guess, I would say it's 4. And why am I guessing 4? Because this is about 80, little less. This is about 320, little less. And I know 8 goes into 32, or therefore 80 into 320 4 times. And Brianna, is it 4? Look at that. Lucky us. It went in nice, no fractions, because what have we only found?
Why?
Because I want to keep moving on, Brianna. I'm just kidding. Not WHY. The Y value. That's right. We found the Y. Okay? We still need to find what?
X.
X and Z. That's right, math family. So what are we going to do now that we have the Y? What are we going to do with that Y?
That Y in?
Where, Rolando? Very good. Where are we going to plug that Y into?
Into the one that has 2 variables.
Ah, very good. Common mistake is people will go back to the original. They're like, oh, I found one. Because that's what we did in the previous section when there was just 2. But if you go and you plug a Y into any one of these, you will still have an X and a Z. And I don't want to have to do all of this again with the 2 variables and 2 equations. So like Rolando said, we're going to pick whatever one we want. And that's why I lightly boxed them so that I could find them easily. And I'm going to plug that Y in either there or there, because when I do that, I've got it down to 1 equation with just 1 variable again. So which one do you think is going to be better, 3 or 1?
1.
Does it matter?
No.
The X, Y, and Z is going to work for any of these equations. That's what we're trying to prove and solve. But very good, Brianna. 1 is definitely the one that I want to use because it's easier. It's already almost got X by itself instead of an 8X. So remember, we got our X plus 12Y equals 47, and we said that Y was 4. So we're just, again, back substituting in what we know. Multiply that out, you get X plus 48 equals 47. And do you have to sit there and subtract the 48 over? Or should you guys be able to tell me what, when I add 48 to it, gives me 47?
-1.
That's right. So we know x now as well. Now, if I got the x and the y, I still need my z, which means none of these have z in it. So now, yes, we are gonna have to go back up to one of those original equations. And you guys have the choice again, because what we're trying to solve is for an x, y, and z that works for all three of these at the same time. If I plugged it into this, it'd be true. If I plugged them into this, it'd be true. It'd be true. So your choice. What can you do to help yourself? Choose wisely. What are we trying to solve for?
Z.
And which one of those equations, 1, 2, or 3, and that's why I name them, just so we can say it easier, would be the best to solve for z?
2.
That's right. We're definitely going to take that one, plug in the x and the y that we found, so we have our one equation with one unknown, and we'll be able to solve for that. So I'll take the 2x plus 4y plus z, that was all equal to 16. And I will plug in, back substitute once more for that x, which we knew was -1, that y, which we knew was 4, and now I should be able to solve for that one and only variable that's left, z. So if you can get to finding that first thing, it's like a snowball from there, right? It's just rolling downhill, catching speed. Pretty easy, okay? But be careful. Make sure you finish appropriately, because there are plenty of places for you to make a mistake. And when I take 14 and add what, do I get 16?
2.
So how do I finish? Remember all the graphs that I was showing you? What did we just find between these three, because they're all to the first power, linear equations, but now in the 3D, 3 dimensions? What did we just find about those three lines?
The triple pair where they all meet.
Very good. It's called an ordered triple, not a triple pair, right? That was an ordered pair because there was 2, ordered triple because now there's 3. An order of the alphabet. Pair because there's 2. Triple now because there's 3. So not order that we found it. It's not 4, comma, -1, comma 2. It's order of the alphabet. So we will put -1, comma, 4, comma, 2. And that is the one and only place that those three original lines would actually intersect. Simple, right? Where can you go wrong, you guys? I mean, look at this. I'll try to show you all of it at once. That's a beautiful mess, right? But again, where can you go wrong? Anywhere. And guess what happens if you miss a negative sign somewhere? When you're distributing this -8 and you don't put -96, everything you do after that is going to be wrong. So be nice, neat, and organized when you're trying to write these things out. Don't try to cram all this on one line like some of you do on your group quizzes and your tests and your homework, okay? Give yourself ample space and make sure you're understanding what you're doing and, more importantly, why you're doing it, okay? So the second example I was going to just start with you all is just to show you how to do that addition or elimination method, okay? When we have a variable by itself, we can use substitution. But very quickly, I wanted to show you guys how we can also use the elimination method, okay? So look down the columns here at your x, y's, and z's, and which ones do you think would be the easiest to eliminate? And remember, we're looking for 2 at a time, okay? Because we're going to eliminate by doing our addition method that we talked about.
1.
Now remember, 1 would be right if we are using substitution, and we would have substituted and solved for that z back into the other 2. You're right, Richard. But my question is, do you want to eliminate these z's, these y's, or the x's?
The y's?
Is there an incorrect answer? No. It is totally up to you what you want to eliminate. Rolando, I really like the y's. Why did you choose those?
Because there's already a positive and negative form.
I could just add equation 1 and 3, and those will cancel out. I'll be left with x's and z's. But if you choose the y's, you have to use all of those, right? I can't go over here and say, oh, well, I could just eliminate the x's next. Whatever you choose, you got to go full throttle at that particular variable, whatever one you choose. But yeah, like you guys said, there's no wrong answer. So if you'd rather do the x's, or you'd rather use the z's, because there's a 1 here, no wrong answer, your choice. Okay? I would probably normally choose the one that has this. But I do like Rolando's suggestion because those are already going to be eliminated just by adding them. I don't have to multiply anything. Okay? But because that's not always going to happen, let me show you what I'm going to do. I'm going to take equation 1 and equation 2. Then I'm going to take equation 1 and equation 3. And I'm going to eliminate them without having to touch the first one. But I am going to have to do something to eliminate those z's from 1 and 2 and for 1 and 3. And remember, we could do whatever we want to an equation. If I want to square the whole thing on both sides, if I want to add or subtract or multiply or divide, take the log. Too soon? Because like I forgot about that. That was way before spring break. We can do whatever we want to an equation as long as we do it equally to both sides. So what I'm going to do to get the z's to be the same is I'm going to have to take this equation 1 and I'm going to what?
Multiply by negative.
Very good. Very good. I'm going to have to multiply it by a negative what?
5.
Very good. To everything though, okay? Not just to the z. That's a common mistake that students make. Like, oh, I'm just focusing on this. No, to keep it equal, you got to do it equally to everything. So that will give me negative 10, negative 20, negative 5, and negative 80. So that means I don't have to do anything to equation 2 actually, right? 2x plus 3y plus 5z equals 20. But then I'm going to have to do something similar over here for equation 1 and equation 3. This one's a little nicer since it's a 2z. I'd only have to multiply by what? Negative 2. But again, to all of it. So that's going to give me a negative 4x, negative 8y, 2z, and 32. Which means, again, I don't have to touch equation 3. I'll write it down as is. And you guys will be amazed at the mistakes that people make with these. They don't even write it down correctly on their paper. Be careful when just writing this down, people get it wrong. Okay, they miss a negative here or they change a number because they're looking at all of it. Okay, just be careful. But notice what we concentrated on was the coefficients of all of these. That's going to come into play a little bit later. Okay, so when I'm dealing with this, I can now take and add, and I'm going to call this equation 12 and equation 13. So I know where these new ones came from. Equations 1 and 2, when I add them, I get negative 8x, negative 17y, those cancel, equals negative 60. Does that look familiar? Those numbers seem similar to me. Negative x, negative 12y, those cancel, equals negative 47. Those look familiar. All right, well, I don't like the fact that all of this is negative, right? But now I got my two equations with two of the same variables. We should be able to finish from here. Okay, if anybody wants me to keep going, I'm more than happy to do that. But once we get to this step, you should know how to finish by using either substitution or elimination. Again, it's totally up to you. You can intermingle. You don't have to choose one and use it all the way to the end. I'm going to take that one and I'm going to paste it right here. That's from the original. This was example number 1 right here. Can you guys see that this equation 3 is equation 1 on this? Can you guys see that equation 1 here is equation 2 here? And equation 2 here is just equation 3 here. Guys, these are the same problems. That's why I was saying, oh, these look familiar. Because if I go back up here and I look, I'll have these same two things. I even color coordinated it. So what do we know we should already get as the answers? So if you wanted to finish this one, by all means do. Just know that they are the same, just in different order. It's the same 3 equations with the same coefficients in front of the variables. Okay? If I had to choose personally, I like elimination a little bit better. As you can see, I got here to the 2 equations, 2 unknowns, a lot faster than doing the substitution method that we did up here, where we had to solve for the z, substitute it into these 2, work it out just to get here and here. Okay, so that's my preference, but again, it's totally up to you what you want to do. Is this familiar? Have we already done it? Yes. It's just adding that extra variable and that extra equation, and therefore having to get back to the 2 equations, 2 unknowns that we know how to solve. Okay, and of course, I'm not going to do this one, but when do they get even more difficult? When they don't give you the 3 equations. Okay, so you will have to take this and set it up. And if you don't know, then go ahead and start with 3 blanks. And for this one, there's a child's cost, so I'd use C, an adult's cost, I'd use A, and a senior citizen, S. If you prefer the X, Y, and the Z, that's fine, but when you solve for Y, you don't know what you solved for. When I solve for A, I know I was solving for the adult number of tickets sold. Okay, so again, it's totally up to you. Just be careful with those. If you need any help, please go see our tutor. Otherwise, I can help you guys at my office hours. All right? So, apologies for the lengthiness, but some of these are just long. So 11.3, We're still dealing with systems in this next section, but now we're not going to have lines always. And since we're just going back to two equations with two variables, they're also going to throw in inequalities. And hopefully you guys remember that when we were dealing with inequalities, when I had something like this, and we solve by subtracting, same way that we always did, right? Now I didn't just get one answer. I didn't say just x is equal to 2 and that's it. Now we have an infinite amount of answers where we then had to show them it's everything from 2, not including it, and greater. And remember, that's when we said 2 to infinity. And if it was equal to, then we would have included the 2 and we would have thrown a bracket around it instead, including it. But what happens when we're not just on an x-axis and we add a second? Well, that means now we're drawing lines. And if we're drawing lines then, and say I did this line, well, just like if it was included for the point, all of these mean that they're included. Well, what if they're not included? What if it's not equal to? Well, then what we're going to do is dash it. And just like this gives me my starting place, and then I go to the right or to the left, this gives me my starting, where it's going to be all of this above or all of this below. Do you guys remember doing this at all? Where you have to shade the infinite amount of solutions, those points, those x comma y's that actually work. Okay, so a lot of similar things, but remember, they're gonna not all be lines. All right, so we're just building off of the previous two sections, the systems of equations with 2 and 3. And again, if you want to read this back on your own, feel free. But here are the options that we could see. Just a few examples, okay? A line and a circle could never touch, which means no solutions. One solution. Give me the x comma y that works for both. Or there could be two solutions where they intersect. Okay? How about two circles? No solutions. One solution. Two solutions. And notice this is actually a, does anybody know the shape of that? Not quite a circle, it's smashed down a little bit.
Oval. Ellipse.
Good, very good. Richard, it's called an ellipse. Anthony said oval. That's what we said back in elementary school, right? We got a little more advanced now. We're going to call it an ellipse. It just sounds a whole lot better. Okay? So yeah, we could have 1, 2, 3 answers. 1, 2, 3, 4 answers even. Yeah, Brianna's excited. Good fun. So, not a whole lot is going to change how we attack it, but the inequality stuff will be a little bit different. Okay? So, let's say we had a parabola, which we worked on graphing a while back, right? If it's strictly greater than or less than, remember these are going to be like those border lines, but now it's that parabolic shape. Okay? And how do we know if it's inside or out? All you got to do is test a point. Just plug in a point. I usually like to use 0, 0. Because when I plug in 0 for x and 0 for y, no matter what's being multiplied, squared, it just cancels it out. So if I plugged in a 0 here and a 0 there, I get 0 is greater than a -4. And is that a true statement? Then that point works. And so does everything else inside. Now, if I wanted to make it a solid line, all I'd have to do is put the equal to underneath it. Okay? If I wanted the other side, still going to have the less than to be dashed. If it's equal to, then you're going to have it solid. But now if it's less than, now 0 is not less than -4. That is not true. So since this point didn't work, we will shade the other area. Okay, so hopefully you guys remember a little bit about that. May need a little bit more of a refresher. Watch some videos, go back and read some more. But these are the types of things that we're going to now be working with. Okay, and if you don't remember how to graph some of those, what are called conic sections, parabolas, circles, ellipses, oh my. We won't get into hyperbola so much, but these are the types of things that we will also be seeing now. And the cool thing is, we don't have to graph unless they ask us to. That's for the inequalities. Okay, so I'm going to show you the substitution method, which for this one, by the way, you couldn't even use elimination. Because notice these are x squareds and y squareds up top, and these are x's and y's. So I wouldn't be able to, even if I multiplied by a negative here, those don't cancel out. X squared minus x is not 0. So be very careful when you're working with these, and remember, you may have to use substitution. So if you don't know it, learn it. Okay?
I have a quick question.
Yeah, go for it, Ant.
Because earlier you said we could do anything to the equation. So why couldn't we just square the bottom equation?
Ah, very good question. Very good. If you square it, remember, is this a true statement?
Yes.
Okay, what if I wanted to square it? Should stay true, right? But can you just square each thing individually? Is that a true statement?
No.
Then no, that doesn't work.
Okay.
So be very careful. What you can do, like you said, is square the whole thing, each side. Because now you can see we have 3 squared and 3 squared. Now we will get a true statement still. So to Anthony's point, if I had x minus 3y equals -10, would I want to square that? No, because that means x minus 3y times x minus 3y. And that will give me x squared minus 6xy plus 9y squared. And now we have this weird thing that this equation up here does not have. So yes, you would be able to get the x squareds, you'd be able to get y squareds, but now you'd have an xy. But very good question, Anthony. Unfortunately, that's not going to be an option for this. Okay? So, substitution. This one is already set up pretty nicely. To find x. And if you want to, again, name them, equation 1, 2, a and b, whatever you want. Okay? The only reason I like to do that is so I don't get mixed up. Don't solve for equation 2 right here and then plug it in here. Okay, that's the same equation. But I will go over to equation 1 now, which is my x squared plus y squared equals 10. And I will substitute in what I know x is. It's 3y minus 10. Now, Anthony asked a good question earlier. We already answered it. What are we going to have to do when we have 2 things squared? Do I just get to square each piece? Unfortunately not. Remember, we reviewed all of this early on. We actually have to take 3y minus 10 times 3y minus 10. Now, if you want to go off to the side and do that or whatever, it's up to you. Okay? But when I do square that out, I get 9y squared. That'll be negative 30y. That'll be another negative 30y for a total of negative 60y. And then positive 100. That then allows me to actually combine some like terms, which that then gives me 10y squared minus the 60y's all by itself. And then remember, I want to get this set equal to 0 because I have both a y squared and a y. And if you guys remember, this graphically is a what? Since there's an x and a y to the first.
Line.
And if both of them are squared and they have the same coefficient, then it is a circle. So we're looking at one of these scenarios that we were mentioning up here, where we have a line and a circle. The good thing is the maximum we can have there is 2, right? Or 1 if it's a tangent, we call it, or none if they don't touch. Okay, but for us, looks like we're going to have to solve this equation, and it looks like we're going to get 2 y's. So we actually want to subtract that over to get 90 equals 0. And those look like big numbers that I don't want to deal with. So the good thing is, because it's an equation, I can do whatever I want. And if I want, I can divide everything by 10. Because it's a constant. Can't divide by variables and get rid of them, but we can rewrite this to look a lot nicer. That looks way better, doesn't it? And doesn't that look like something that we can solve? By doing what? What was the quickest, easiest way that we learned first to solving these quadratic equations?
Factoring.
Very good. Excellent. Factoring. So I'm going to factor this. Y times y. Same and both negative for my signs. And I know 3 times 3 multiplies to positive 9 and combines when I add them to negative 6. Which gives me actually only one answer for y. Even though it looked like it was going to be 2, it happens to be the same. And am I going to write it twice? No, that's silly. So that's the good news, is I found my 1y. And if you guys remember, at the very beginning, we already found what x is. Our x was equal to this, but it had a variable in it. But now we know that variable. So we will do just like we did before and back substitute into equation 2 to find our x. It's 3y minus 10, and we found that y to be 3. So we get 9 minus 10, which is an x of negative 1. So how do we finish? What do we put? Our final answer? 3 comma negative 1, right?
No.
What do you mean? That's an ordered pair. I found this first and then that second. That's the way I put it, right?
It's x and y, not y and x.
Very good. Remember, it's the order of the alphabet, not the order that you found it in. Okay? So negative 1 comma 3 would be, if we graphed it, which you can go on to Desmos or whatever graphing calculator or whatever you might have, and graph these 2 points or 2 lines. Okay? Excuse me. 2 equations. That circle and that line, and you guys would actually know exactly where they intersect. Okay? So, can we use elimination? Sometimes. Only when the variables are the exact same and the coefficients are a little different. So this one should be pretty easy. Just be careful. What should we do first here?
Multiply the second equation by negative 4.
Good. But I'm going to make it even easier for you, Brianna. I'm going to multiply it by negative 1. Because it does not matter which variable I eliminate. I don't have to eliminate the x. And rather than having to do a negative 4 to all of this, I can just do a negative 1. Because these are the same coefficient, just different sign. And that will get the different sign. Okay, so I'm going to take that equation 1 as is. 4x squared plus y squared equals 13. And my new equation 2, which made it all negative values now, And now I will add those to get rid of one of my variables. Again, guys, the name of the game is getting it down to one equation with just one variable. And now we have that. And now we can hopefully remember how to solve. Be careful. This is where a lot of people make mistakes. They know to divide by 3 to get the x squared by itself. They know to then take the square root of both sides. But remember, what should you be putting since you did the square root?
Positive or negative?
We need the 2 possibilities, the 2 answers that I could plug in. When I square it and multiply it by 3, I get 3. And that would include, when I square it, I get 1. And that's both a positive and a negative 1. Which this is where it gets a little funky. That right there tells me I have answers of 1 comma something and negative 1 comma something. We need to find that other thing, that y value. Unlike the previous problem where we used substitution, we solved for something, then plugged it in, then went through and solved for one of them, and then back substituted it into that to solve for the other. I don't know what y is equal to in either of these. So unfortunately, I'm going to have to choose either one, the easiest one, to then solve for the y. And what am I going to do first? Equation 1 or equation 2? What do you think would be easier to solve for y?
Equation 2.
Definitely.
The number 2.
Definitely. Let's take equation 2, which is, careful, in x, which we know, so I'm going to put parentheses, plus y squared equals 10. I'm not going to take the other one where I multiply by negative. I'd rather use the positives, okay? Even though they're the same. And I know that our x is, oh shoot, wait a minute. It's both positive and negative 1, isn't it? So can I put in plus or minus 1? Is it always going to come out the same for a positive 1 as it is a negative 1? Not always. Very good. So be careful. Do one at a time. No pun intended. Okay? If I plug in that 1 and square it, what do I get? Well, that's obvious. It's 1. But now I got my 1 equation with 1 variable now. I should be able to solve. But how many answers for this x of positive 1 are we going to get for y?
2.
We're actually going to get 2 answers. That's right. So check it out. Be careful. I'm going to go ahead and subtract the 1 over. Get y squared equals 9. Then I'm going to take the square root. And remember, if you take the square root, you have to put the plus and minus possibilities. When we undo that, we get the y out. And when we take the square root of 9, we get 3. So that was for my x equaling positive 1. So I'm going to have to go over here and put both 3, and I'm going to have to put a negative 3 for that positive 1. Now, guys, does that mean we have to hit the reset button and do the exact same thing over here for the negative 1? Kind of. Because check it out. What are we going to get when we square the negative 1? The same thing, which means I would end up doing the same thing here and canceling, and then taking the square root and cancel to get my plus and minus 3. So don't be robotic. Use your mind. That's why you have one. That's why we'll always be superior on Earth. Maybe not always. These robots are getting crazy, aren't they? But we know that we're going to get the same thing whether we put in the positive or the negative 1 because we're squaring it. So we don't have to go through this all again. We know we're going to get the same 2 values for negative 1 would be 3 and negative 3. But that gave us a whole solution set, which a lot of books will write them all in here like that. I don't care for it. It's fine. You guys don't need to do that. Of all 4 of these things. Okay, so I did want to show you one with substitution, one with elimination, just to make sure. And then let's make sure that we know how to graph these things as well. All right, and then that'll be it for those. Almost done. How do we graph? Well, oftentimes we want to get one of the variables by themselves. So I'm going to add the y over so that I have a y plus 1 where the mouth is open towards those, and then the x squared on the other side where it had its back to the x squared. Then I'm going to go ahead and subtract that 1 over. And now I have y is greater than or equal to x squared minus 1. Hopefully you guys recognize that. That is a parabola. Y equals x squared minus 1. And if you remember, this was the parent graph. That y equals x squared that we should know and love. 0, 0, 1, 1, 2, 4. And then same thing on the other side. It's this, but what?
Down 1.
Shifted down 1. Very good. It's not being done to the x squared part, so it is going to affect the y. And remember, y's are y's. We do what it says. X's are x's because they wanted the opposite of us. Okay, all that still applies. So that means all I'm going to do is shift down 1, and I'm still going to go right 1 up 1, left 1 up 1, over 2 tick marks, up 1, 2, 3, 4, over 2 tick marks, 1, 2, 3, 4. It's still just our x squared. Okay, before I graph this though and just draw it, I need to look because we didn't have the equal to. But do we have the equal to in this inequality? Yeah, and because it's equal to, that means I would draw it just as if it was equal to. In other words, it would be that solid line or curve. But that, remember, only tells me where everything is for the x's and y's equal from the right to the left. Okay? If the equal to was not there, then I would have dashed that parabola. But how do I tell about the greater than parts? Because out here, the x is greater, but up here, the y is greater. Right? Remember, all we got to do is?
Plug in a point.
That's right. Choose a test point. And what is my favorite test point?
0, 0.
0, 0. And if it comes out true, then not only is that a solution, so is everything else in that area. If it comes out false, where this is not a true statement, then this was not a solution, which means nothing in here will be, so everything out here will therefore be. Okay? So at that point, 0, 0, we're going to test it into this, and that would give us a 0 is greater than or equal to 0 squared minus 1. So is 0 greater than or equal to a negative 1? And therefore, since this did work, we know everything in here also will. That's it. Pretty simple stuff. You guys may have to do some rehashing on a few of these. I even put a part B when there's multiple things, like a line and another line. Hopefully you guys know if you graph one line and you shade this side of it, and then you graph another and you shade this side of it, what's the only area that works for both?
The one that shaded twice.
That's right, in here. So this is what you would shade. Not any of this or this, because that only works for each individually. So we're looking for where it overlaps completely. Okay, if anybody wants me to do that one, we can, but I'm just worried about time today. we're not going to have any time to do the group quiz, which is why I will give you guys until Friday. Okay, if you guys need till Sunday, I'm fine with that too, but I just want you guys to have some time to work on those. We're all good? Okay. All right, then I will go to the next section, which is 11.5. And this is where we introduce these things called matrices. Okay, so do you guys remember synthetic division? Remember how we just kind of got rid of the variables and we just took the coefficient numbers? And that's how we were able to do long division fast, nice, neat, and quickly? Well, again, this section is going to basically be doing that. Okay, it's very similar to synthetic division, but now for all these systems of equations. Right? So again, I pause here so that you guys can pause and read through it if you want to watch it back. All right? But a matrix is when we have one. Matrices is when we have multiple. Matrices. See, it just sounds funny. Okay? So what we're going to be doing is still multiplying. As long as we do it to both sides, right, we can do whatever we want. And that equal sign that we didn't really have when we were dividing and using synthetic division will still be there. It's just going to be this long line, vertical line going up and down, and we will therefore call it an augmented matrix. Okay? No big deal. Just wanted to put some of this forward to you. The pieces inside of these matrices are going to be called elements, and they list them like this, where A represents any number, and the I and the J subscripts down below represent the rows and columns. Okay? Rows and columns are going to be our equations and our X, Y's, and Z's for these things. Okay? And we're just going to deal with these things the way we read, left to right, top to bottom. We'll learn how to add, subtract, multiply with these. Okay? And then ultimately, we're going to use them to solve. So if I give you a matrix A and a matrix B, or C and D, and I add you to add them or subtract them, you're just going to take the same row and column elements and do that thing to get a new one. Subtract the same to fill it in for a new. Okay? And remember, the order does not matter with these. It can be left to right or right to left with the A and the B. Or add them in any order that you want. Okay? We won't deal with this much, but if you guys get into higher levels of math, here's what they look like. Okay? This matrix A, I have row 1, column 1. So this would be A11. This would be A12. This would be A13. Row and then column. Okay? If I ask you to add or subtract, what are you going to do? Call this part A. Let's add them together. And what would we do to get that first element, that first row column element in this matrix? If I'm going to add. Well, I would just take this and this, which are in the same places, and I'd add them like Eve. Okay, if I'm going to add them, what's 4 plus 2?
6.
Good. Then do the next element over. Negative 13 and 0. 9 plus a negative 6. It's literally that easy. It's just weird looking. It's different. Okay, and there are applications that we will get to today a little bit later. Okay, so adding those up, I would get 8 for the next row, negative 7, and 10. Slow me down. Let me know if you need me to explain that. How about the next row? What's the first element going to be?
-10.
Then what?
9,
9.
And
7.
you're like, hold on, let me get my calculator. Good, Brian. 7. Okay, that's it. Now, when do we have to be more careful, obviously? When we're asked to subtract. That would be part B. Okay? What are we going to do? Same thing, but order does matter with subtracting, right? Not like adding. If I took 4 plus 2 or 2 plus 4, we still would have had this. But 4 minus 2 is what we're going to get for this first one. But 2 minus 4 would be a -2, different. Okay, so be careful with the order. You guys all good with that? -13, what would the next one be? Quick.
15.
Good. I tried to rush you guys because I wanted to see if you'd make a mistake, because that's usually when mistakes are made, when people are rushing and not paying attention. We are taking this and subtracting a negative. And remember, when you subtract a negative in your life, that's a positive thing. So we would have a -6, which becomes a +6 to that 9, which is where we got this. Okay? So I'm not going to finish that. I mean, I think you guys got it down. Pretty simple, adding and subtracting. But there's some more terminology that I'm going to add in here real quick. And there's this thing called a real number, a constant, that has a magnitude but not a direction. None of that will make any sense to you until and if you take physics, okay, where we actually have these things called vectors. Some of you guys may remember these terms from Math 4A if you've taken it already, and that's trig. If not, you will come across it at the very end of it, okay? But this is called a scalar, okay? It's just a number, a constant, okay? A scalar, if you ever see that number. That's how we denote a constant, a number, when we're dealing with these matrices. Okay, so if I gave you this, which we would call a 2 by 2, that's how we say it very quickly. 2 rows, 2 columns. And I wanted you to make it bigger or smaller. I said, I want you to multiply it by some constant, some C. Again, they're just calling that a scalar because it has further applications in physics. Okay, all you do is take this and just like you would anticipate, you're going to distribute it to everything. It's that easy. Okay, so when I put 3a, what would you do to that and all of these numbers in here?
Multiplying by 3.
Multiply what by 3?
Each element.
That's it. Everything. What if it was a -3? Just be careful with your signs. Okay? Don't make this stuff harder than it is. If I put it all together and I have you multiplying and subtracting, could you guys handle that? You're like, I don't know. You're just showing this to me and I get it, right? But yeah, I think you can handle it. What would you do first? Multiply all of this by 5. Every single one of these elements, we call them. What would you do to B? I would actually multiply it by a -3 so that I could just add rather than have to multiply by 3 and then subtract everything. Just get the subtraction over with by distributing it, okay? Because this would be a little bit easier than that. I always prefer adding over subtracting, okay? I think you guys can handle that. I'm going to keep moving on because multiplying is a little bit more difficult in that it's not as intuitive. It's like, yeah, that makes sense. Multiply by a constant, a scalar, cool. Do it to everything. Add, subtract, only the things that are in the same spots. Got it. But multiplying these matrices is a little weird. We can take a 2 by 3, they're calling A, and we can multiply it to a 3 by 3, they're calling B. The only thing I want to highlight here is that, grab the highlighter, the color that you guys can see, these right here, no, it's not really letting me, right? All right, I'm not going to highlight it. These have to be the same. Okay, as long as that works, then we will be able to multiply. Okay, so what it's going to look like for those, I'll leave that one above here. My 2 by 3 to the 3 by 3. I will take this row in this column. So you can see the A1, 1, 1, 2, and 1, 3. And I will multiply those to everything here that matches up. So B1, 1, 2, 1, and 3, 1. So I'll still do the first two things first, the second two things second, and then the third element third. But what I will do with all of those multiples is I will add to get my new 1 term or element. Okay, so that's a little bit weird, a little different, but you're basically just going to take this row and multiply it with this column to get a new term up there. Okay, and as you can hopefully see, when we multiply a 2 by 3 to a 3 by 3, what will the result yield? A 2 by 3. Okay, so is it commutative? Is it associative? Can we still distribute that constant? Well, as you can see, yes, it is still associative. We can do these two and then that, or these two and then that. Can we still distribute a constant? Yeah, we can actually distribute a whole nother matrix. Okay. But notice it is not commutative. The order does matter with that. All right, so I just wanted to show you one example. Let's say we had a 2 by 3 and we wanted to multiply it to a 3 by 2. And let's just do C and D. What would we do? How would we get this matrix? All we'd have to start by doing is taking the first row with the first column. And I would start by multiplying the 3 and the 4. I'll write out the whole thing. So I'm going to have a 3 times a 4 plus, now I'll do the second of each row and column, 6 times a -2. And then the last one, which would be a 4 times a 5. So I took this row for the first, second, and third, and I multiplied it with this column with the first, second, and third. And that all together, after I find each product and add them together, will give me my first element in my new multiple. Okay. Now I'm going to take that and I'm going to do it to row 1 with column 2 now. So I will take that row 1, column 2, which will give me my first row second element. By taking row 1 and column 2, that'll give me this element. Sorry, so much red there. So then I will take the 3 times the 10 this time, plus the 6 times the 6, and then the 4 times the 9. Okay, and then what am I going to get? Well, I did this row with this column for here, and then I did that row with this column for here. So the only thing we haven't multiplied now is this row with this column and that column. Okay, so now I'll take the negative 8, 0, and 12 and multiply it with my column over here. So I'll get negative 8 times the first thing, which would be 4, plus the 0 times the negative 2, and then the 12 with the 9. So all of these with all of these, first, second, and third, first, second, and third. Okay, then I'll do the same thing with this row now for my second. So we're finding the second row and the second column, its spot, by using the second row and the second column. Guys, seeing how the numbers kind of work for the element in the rows? So negative 8 times 10 plus a 0 times 6 plus a 12 times a 9. And if you guys like puzzles, that's what these are. Big, nasty puzzles. Go ahead, Heather, I'm sorry.
You put the 9 twice. On the first one, it should be a 12 times 5.
Oh, thank you. Yep. Very good. Just checking you. So now what do we do with those things? We multiply them out and add them up. So I'll get 12 plus a negative 12, which that's nice. Those cancel out, plus 20. So my first row times my first column gave me that first element, 1, 1 of 20. Over here, 30 plus 36 plus 36. So that together is 72 plus a 30 for 102. We're multiplying. Things are going to get bigger. All right. And then this one, negative 32 plus, I like that one, 0 plus 60. So 60 minus 30 is 30. Minus 2 more, be a 28. Negative 80. There's my 0 again. Plus 36. So it's definitely going to be negative. 80 minus the 30 would be 50. Minus 6 more, 44. Okay. So that is what we ended up with as our new multiple here of C times D, they called it, this new matrix. Right, a little different, definitely weird, gonna take some getting used to, but hopefully you guys understand how we're doing it. Okay, just taking rows with columns to get that element for row 1, column 1. All right. So are these things possibly not defined? Yes. We would not be able to do the 3 by 4 times the 4 by 2 would be fine, because the inner match up. But if we switched it around and try to do the 4 by 2 times the 3 by 4, notice these would no longer match up. And since they don't match up, we won't be able to use this case. We'd have more things to multiply or not enough things to multiply to. And so we wouldn't have enough. Okay? So, I know it's been a long time. Hopefully you guys are doing okay. This last section here for today is we're going to wrap it all up with this thing called Gaussian elimination. Okay? Gauss is a famous German mathematician that I grew to hate as I was going through my math degree at Fresno State, because he did so much, and he did so much at such an early age, and some things were just mind-boggling. Very, very brilliant person. Okay, one of his first contributions was in 3rd grade when his teacher told him to add up the whole class, add up everything, every digit, every number from 1 to 100. And then the teacher sat back and put his feet up on the desk, thought he bought himself a good 15 minutes, but not about 60 seconds, maybe 3 minutes later, little Frederick Gauss walks up and he hands him his answer. Brilliant, brilliant mathematician. Okay? What we're going to be doing in this section is using what he came up with as kind of like our synthetic division for solving those systems, as I mentioned in the previous section, where we're still going to have those 2 equations, 2 unknowns, or 3 equations, 3 unknowns. But as you guys hopefully noticed, we ended up just concentrating on the coefficients. We didn't really focus on the x, y's, and z's. It was the numbers that we're trying to eliminate. Well, then he just got rid of the x, y's, and z's and said, well, then let's do it in this matrix sort of way. Okay? So little of what we're going to be dealing with here is when we have this matrice set up here, where this is my x, y, and z coefficients for all 3 equations. Equation 1, equation 2, equation 3 are now my rows. There's going to be a line that they're going to put, and that will be the numbers, the coefficients on the other side. That line is going to represent the equal sign on our equation. In our goal, what Gauss figured out was, well, if these are all the x's, the y's, and the z's, I would really like one of my equations to have a 1, and another equation to have a 1 for the other variable, y, and another equation for the z, because that's what all of these represented, was the x, y's, and z's. And if I can get that diagonal, where I have an x, a y, and a z that are all 1, and everything below that diagonal I can make zeros, then if this is the x, and this is the y, and this is the z, what does that mean that this just solved for us if we have the equals a number on the other side? We just solved for z. And therefore, if we know z equals some number, well, then I can plug it in here, because that's what this number of z's represented. And if I plug it in there, now I have my y all by itself. And now we can solve for y. And since I now know my z and my y, I can plug it in there and plug it in there. And now we can solve for our 1x. Beautiful. Done. Without even seeing the x, y's, and z's, because these will all be numbers, or coefficients of them. Okay? So that's what this explanation is basically just saying that's what we're trying to obtain. The diagonal of 1s, everything below it, zeros. Don't care about these numbers, we will just deal with them. Okay? That's it. Let's see how we can do it. Does this look familiar? This is what we did in 11.1, which was the week before spring break. All we're going to do is take this and we're going to rewrite it in what is called that augmented matrix. And that augmented matrix means, you know what? Just get rid of the x's and y's. So what's my first row going to look like?
4, 3, and 11.
Good. But how do I know if this is an x, y, and z that it's supposed to be representing, or if this is the x, this is y, and this is what it's equal to? Well, that's what it means by augmented. All you're going to do is draw a little line separating the two sides of your equation. That's it. That's the only difference. What's row 2 going to look like?
1, -3, -1.
That's it. And what is our goal? What are we trying to do? Get a row of 1s, and then everything below it, 0s. Now remember that earlier, no, we've been going for an hour and a half straight. But if you guys remember earlier, I switched a 3x3 that we had, 3 equations, 3 unknowns, and I moved them around and I switched the order and I called it example 2, and I did elimination with that. Well, does that mean that if I wanted to start with a 1, couldn't I just flip-flop these 2 rows? Couldn't I have done that here? Couldn't I have just written it differently, Brianna? Couldn't I have written this one on top and this one on bottom? So then guess what I can do with these 2 rows? I can switch them. Guys, everything that you know about equations and how you can multiply, add, subtract, do all of those things, it all applies to this. The only difference is it doesn't look like that, it looks like this. It doesn't have this involved. We're trying to clean it up for when we get to the 3x3s. Yeah, then it gets uglier. Okay, so I'm going to go back here and I'm going to just rewrite it. And I'm going to just write it as 1, -3, -1, 4, 3, and 11. You guys cool with that? All I did was switch row 1 and row 2. And that's how we show them how we got all of a sudden from the green to the blue. You're just supposed to tell them. Okay? So now I got that leading coefficient of 1. Well, now I want to get this to eliminate. And you remember what we try to do when we eliminate variables? We had to multiply this whole thing by something, and then we added it to cancel that out. We're still doing all of those things, just without all the letters, the variables. We're cleaning it up. So I'm going to tell you what I'm going to do on this next one. I'm going to multiply row 1 by -4. And I'm going to add it to row 2 to get a new row 2. And that's going to give me this new one here. So I'm showing you what I'm going to do to this to get that new matrix. Okay? So what I like to do is actually use the previous one over here so I don't clutter my new one that I want. So I'm going to take row 1 and I'm going to multiply by -4. And then I'm going to take all of those things, which is just this equation. I'm just multiplying that whole equation by a -4. And then I'm going to add it to row 2. So I'm going to put it right underneath it. That's going to be a -4 when I multiply to there, a +12, and then a +4. And then I'm going to add that to my new row 2 here. And when I add that, what do I get here for my first element?
Zero.
Good. Now, notice I put my row 1 up here. Did I say I'm going to change row 1? No. I used row 1 to get a new row 2 by multiplying this whole equation by -4. But then we're going to take that and we're going to add it to my row 2 to get 3 new elements for this second row or equation. So very good. Anthony said we're now going to have a 0 there, a 15, and a 15. And so therefore, what can I do to my new row 2?
Five times row 1.
Actually, I'm good with row 1. I got the 1 here. I need my diagonal. I need this to be a 1.
Multiply row 2 by 1/15.
Very good. I can multiply by that 1/15, which is the same as just dividing by 15, like Anthony said. So I'm going to take row 2, and I'm going to multiply it by 1/15 to get a new row 2. Not touching row 1 because I like the form that it's in, but when I divide all of this by that 15, or that 1/15, I get 0, I get 1, and I get 1. And remember, this is just my new equation, which says how many x's do I have? Zero. How many y's do I have? And it's equal to what? So then I know that this is telling me that I have 0x plus 1y equals 1. In other words, y is equal to 1. And if I now know what y is equal to, then can't I use that equation 1, which says 1x minus 3y equals -1? And can't I plug in what y is? Just like we did before, x minus 3 equals -1 and solve for it? Yeah. Add the 3 over, or just tell me what minus 3 gives you -1. And how do we finish? What do we put in our answer blank? What did we just find about these two lines? We just found the point of intersection. That x comma y. Guys, if you don't quite understand what the heck I just did, remember, you can still solve this using regular old elimination, not Gauss's method. You could have multiplied this whole thing by -4 and got 4x plus 3y equals 11 on top, -4x plus 12y equals 4 on bottom, added to get your 15y equals 15. Does that look familiar? It's exactly what we had here. You're like, why, Alan, would I ever do all of this matrix stuff when I can just dodge it and do the stuff that I already know? And you're absolutely right. And I don't blame you. But remember, this is part of this course, is that we learn these new techniques because it can come in handy instead of having to do substitution or elimination with this. Okay, so I just want to go over this very quickly with you. One last time. How are we doing on time? Cutting it close. How do we rewrite it? Well, you know what? I'm not going to just write 3, 2, -1, -10. I already am going to switch these around a little bit. I'm going to take this and I'm going to write it as my row 1 because I like that it already starts with a +1. So I'm going to call this row 1. I'm going to call this row 2. And then I'm going to have this be my row 3. You guys okay with that? I'm going to do some jumbling already. So now I have a row 1 of 1, -1, 2, line 7. Remember that line represents the equation. Okay? Then I'm going to take row 2, which is -1, 3, 1, -2. And then row 3, which is that other equation. And I'm going to put a 3, 2, -1, and -10. Now there is a whole class that deals with this kind of thing. It's called linear algebra. Math 17 at our school, okay? Where we go 4 by 4, 5 by 5. Yeah. For us, this is where we're going to stop, is with these 3 by 3. Okay? These 3 equations, 3 unknowns. Augmented matrices. But remember, the goal is to get these to be what? Ones, and everything below it, zeros. Now, there's one that you can do that's even further. Our book doesn't go over it. It's called the Gauss Jordan. And Jordan came along and he was like, oh, I can do you one better. You know what? You did this as all the ones and these all as zeros. You know what I'm going to do? I'm going to take everything above it as well. These were all ones. These are all zeros. For Gauss, Jordan said, I'm going to take these up here as well. I'm going to make those also zeros. Now that requires more of the matrix stuff. But if you do that, and all of these are ones, and all of these are zeros, then if you just have 1, 1, 1, and a bunch of zeros everywhere else, and you have this X, Y, and Z for the numbers, then I shouldn't have used X, Y, and Z, A, B, and C, then you know X is equal to that, Y is equal to that, and Z is equal to that, without having to do any back substitution. So if you wanted to take it further, I wanted to at least mention that, okay? All right. Let's do a little bit of this, okay? I already know I'm not going to touch row 1. I'm good with that leading 1, which is why I rearranged it. But I now want to make this a 0. Always try to get your zeros before your ones, okay? And how can I get that to be a 0? Very easily. Just take row 1, add it to row 2 to get a new row 2. So I'm not going to touch row 3 just yet. I'll go slow here. But I am going to get a new row 2 by just adding these together. I didn't even have to do any multiplying because these were already opposites. So that then is going to give me a 0, which is what I wanted. And then I just deal with the rest. A 2, a 3, and a 5. All good? Next, I want to get that 2 to become a 1. So I'm going to have to do what to this whole thing?
Divide by 2.
Yep, unfortunately. So I'm going to take half of row 2 to get a new row 2. So again, only changing row 2. That will not have changed. This I haven't attacked yet. But by taking half of all of these, I still have my 0, which is why you have to get the 0 before you get the 1s. 1. Oh man, fractions. Hopefully we don't have to touch that anymore. Okay, now what? What's my next goal?
To get the zeros in row 3.
Good. I like how you said zeros. I want to get both of these to be zeros. So I'm going to start with this first one, and then I'll go to the second one. Then we'll work on this becoming a positive one, and then we'll have it. We're done. Very good. So I'm going to take row 1. I have to use row 1 because that is never going to be able to get rid of that 3. So I'm going to take row 1, and I'm going to multiply it by what?
Negative.
Good. Negative 3 times row 1. I'm going to add it to row 3 to get my new row 3. So row 2, I'm not going to touch. I'm going to write it all down again. The only thing that we are changing is row 3, and we told you how we're going to do it. So I'm going to just do it up here. I'm going to multiply this whole row 1 by negative 3, and I'm going to put it right underneath this to get my new one. So that's going to give me a negative 3, 3, -6, and -21. Does everybody understand where I got these numbers from? I'm multiplying row 1 by a -3, but then I'm going to add it to row 3, so I'm putting it right underneath. So -3 times that gives me -3. -3 times that gave me +3. -3 times that gave me my -6 and -21. Now I'm going to add this, which zeroes out, which is what we were trying to do. That's why we're doing all of that. Brianna said, this gives us a 5 when we add it, a -7 when we add it, and yuck, a -31. Now, my next step, I will take and I will rewrite it once again. In order to get this to be a 0, I'm going to have to use equation or row 2. Because if I go back up here and I multiply it and add it to this, I'll get rid of my 0 that I originally had. Okay, so I'm now going to have to use row 2 and do what to get rid of that?
Multiply by -5.
-5 times row 2. I will then take that and add it to row 3 to get a new row 3, which means I am again not changing rows 1 and 2. I am using row 2, but to get a new row 3. So multiplying all of row 2 by -5 would give me a 0, a -5, -15 halves, and -25 halves. Oh, man. Almost didn't have to touch those fractions, but here we are. Don't stress too much. First two are easy. That's a 0. That is also a 0, and that's why we did what we did. But this and this, we're going to have to go off to the side and do a little bit. -7 over 1. When I subtract 15 over 2, I'm going to have to multiply this by 2 over 2. My fancy one to get -14 over 2, still -7, right? Minus 15 over 2. So I get -29 halves. I know, not the best. Okay, then over here, -31, I was subtracting 25 halves. So I'm going to have to multiply this by that fancy one again. So -62 over 2 minus 25 over 2, which gives me -87 halves. Again, don't stress. Here's why. What can I do to this if I wanted to get rid of those dividing by 2's?
Multiply by 2.
I could multiply this whole thing by 2. And that's going to give me nothing changed up here to those 2, but doubling all of this would just cancel those out and keep my zeros. And what do I want that -29 to become?
A 1.
So what am I going to do to that whole row 3, that equation 3? I'm going to divide the whole thing by that -29, which will still be a 0, but now this gives me a +1, and this gives me positive, I don't know, what does it look like? Kind of a 30 and a 90, maybe 3. Brianna still doesn't trust me. It's 3. Which means what, guys? Why did we do all of that?
To find X, Y, and Z.
Some of you guys are like, because you hate me. It's not me, you guys. I'm like channel 47. I'm on your side. Okay? I'm trying to help you through this. That diagonal of 1's, now represents this equation here, means we don't have an x or a y, we only have the z. And therefore, since this is our equal sign, we just found z is equal to what?
3.
Beautiful. Now it took us a little bit of work to get there. Not too bad. Not too bad. Brianna, if you want me to go back and show you the 3 equations, 3 unknowns that we did with substitution and elimination, that really isn't that bad. It's actually a little bit more clean, in my opinion. But you've never done this. You've done elimination substitution, so it feels a little bit easier. This, you're like, that looks like your background, Alan. Just a bunch of zeros and ones and numbers all over the place. I don't know. It's like it's sucking me back into that tunnel. I get it. This is different, but give it a chance. Okay, you can try it this way. Ultimately, I need you to solve this problem. Do I care how you do it? Substitution, elimination, or even this Gaussian matrix setup. It's up to you. I'm not going to penalize you guys for doing it correctly. What I will penalize you for is you doing this and not any work. You're going to have to show me something. Whether it's this way or not, I don't care. Okay, but please try it. Challenge yourself a little bit. All right, and again, once we found the first one, then it's all snowball from there. It just plug it in, we're good. Okay, plug in the 3 there, work this out, and remember, what does that mean? That I have y plus 3 halves of my z is equal to 5 halves. And all that's going to change when I plug in that 3 is that I have y, sorry, that wasn't very good, y plus 9 halves. And what's going to happen when I subtract that over?
I have -2.
Negative 4 halves, which, very good, is -2. We just found our y. And once we have that, we will lastly take our what? One x minus 1y plus 2z is equal to 7. And we will plug in what we know each one of those things is. The y, careful, put them in the right places, was -2, and the z was 3. And I always put parentheses because should you be subtracting the -1 and 2? No, remember they're multiplying. Okay, so that would give me x, multiply those, plus 2, plus 6 equals 7. Or x plus 8 equals 7, so what's x? Which means my answer, how do I write it? What do I put in my answer blank?
-1, -2, -3.
Guys, it's as easy as 1, 2, 3. That's where I would drop this pencil if it wasn't so expensive. Okay. So that's it. I know we went very long today. I even went a little bit over, but I wanted to make sure that you guys got an in-depth approach at every single one of these sections. So no breakout rooms today, but I wanted to make sure that I went into this because it is very different than what you've seen in the past. Okay?